Welcome back, guys. This is day 9 of rotation dynamics. And in yesterday's class, not yesterday's class, in the previous class, I've discussed problems where the body is linearly accelerating and angularly. It's accelerating in both ways. It's linearly accelerating and angularly accelerating. We simply split it into two different forms as separately linear acceleration and separate angular acceleration, and we've done this kind of problems, right? And to just remind the stuff that has happened yesterday, I'm going to give you one more problem based on that old idea only. I want you to do this problem once, and let's slowly get into the topic. Okay, so there is a disk, no hinge, it's not hinged, it's completely free, and a force is applied at a distance r by 2 from the center. Force is applied at a distance r by 2 from the center. I want the acceleration of this particle. What is the acceleration of this particle? Not just linear, the total acceleration. Okay, the final acceleration of that particle. Do some quick math and try to bring the answer as quick as possible. Okay, I'll just do it anyway, but you have to try it. Just remember that we are dealing with a linear acceleration and an angular acceleration problem. So you just write the linear equation and then angular equation, and that's all. You can give me the answers meanwhile. When you are doing it, give me a linear acceleration, a center of mass separately. Of course, I should give the value of masses and forces, right? So the force is F and mass is M. You can directly give me the center of mass acceleration, alpha value. Center of mass acceleration can be given, alpha value can be given. Aditya already gave an answer saying, I don't know, I don't understand the value, but RF by M, why do you have an R there? So what do you do, guys? I'm doing the problem. Meanwhile, if you get the answer, it's fine. Okay. So because of the linear force, it's a center of mass that has an acceleration, which is nothing but F by M directly. And it's a summation of that plus with the torque that is applied. There is an angular acceleration also. So how do I find alpha? F into R by 2 is nothing but I alpha. Like I mentioned, if it is not hinged, you simply take it. Linear is 4F by M. Mazida, why do you say 4F by M? Linear is F by M. There is only one force acting on the body, F. That's all. So the torque Fr by 2 equals to I alpha. So F into R by 2 equals to, like I mentioned, moment of inertia I is always mr square by 2 into alpha. 2 gets cancelled, R gets cancelled. F equals to mr into alpha. So alpha equals to F by mr. Alpha equals to F by mr. Now clearly observe what I'm going to do. Is the moment of inertia correctly taken? Yeah, it is mr square by 2 only. So the body has, I'm sorry. So the body has a combination of linear acceleration and an angular acceleration. In the linear acceleration, every part of the body has F by M basically. That is the acceleration, F by m only. But because of alpha, all the particles has r alpha, r alpha, r alpha, r alpha. Okay, let's write the value of r alpha. If only I multiply alpha is this, r alpha is nothing but f by m, f by m, f by m, and f by m. So when I combine them, when I combinedly write the acceleration of both the particles, what do I, sorry, both the situations, it has f by m because of linear. So all the points basically has f by m linearly. This is from the linear motion, guys. And because of the angular motion, I'm going to write, watch this thing. I'm going to add all these four values here. So f by m, f by m, f by m, f by m. So that is right, guys. These two gets added, they get a resultant. The acceleration of this part is zero. People already gave me the answer saying they're getting zero as the answer. So the answer is zero for that, and this also resultant. But I asked the acceleration of the topmost point, so the answer is basically zero. That's a good. I mean, like I intentionally gave that value. Yeah, tell me, Aditya.
Sir, is this the case of a frisbee when we throw it?
Not exactly. Not exactly. They could be. I mean, you could literally hold the frisbee at any point, and it can change all the situations. So no, you cannot say that. It's not exactly that, but you just solve the problem in these kind of manners. Okay.
Yes, sir.
Now, so once you clearly understand, remember, I mean, like clearly get the point how to find when the linear and angular accelerations are involved, we can get into better problems, we can get into bigger problems now. But I want to discuss this specific model that is very occurrent, like it occurs a lot. uh, Let me take black. Basically, this is the main, like a normal kind of a problem whenever you have a pulley, mass 1, mass 2, moment of inertia, and we solve the problem normally. There is nothing strange or nothing new in this kind of a problem. No, I'll tell you something new in this problem right now. It is connected, the string is connected, but the pulley is like this. That's it. This is the diagram. The pulley is not fixed. What happens is, like, the rope is actually wrapped around the pulley like this, and it is released. What happens in this kind of situation, it unwheels, it unwounds, and along with that it parallelly accelerates. You understand the situation. You take a pulley or a disc, you wind it with a string, you connect it to the ceiling, and you release it. It unwinds and it actually moves downwards. So there is a problem. This problem is easy, quite easy, like we can happily do this kind of problem. But this problem is a different model, so I'm going to discuss this idea. Okay. uh, Let me just explain it easily first of all, and then we slowly get into the big part of this topic. So this is how the police, yeah, like exactly like yo-yo. Aditya, you're right. You're basically taking everyone. I hope everyone knows what a yo-yo is. If you don't, after the class, please go ahead and Google what a yo-yo is. So you wrap around a string and you pull it. So except it's not pulled, it is just simply fixed to a wall up there. Now mass is given, so mg is acting downwards for sure, tension is acting upwards, and the body is accelerating linearly, and the body is also accelerating angularly. That is an important point here. The body is accelerating linearly, and the body is also accelerating angularly. So I'm going to write both the equations, linear equations and angular equation. For linear equation, basically mg minus t equals to mass into acceleration. That's all. For angular, I'm going to take the talk about the center of the disc. Sir, Jackie Chan ties a rope to his waist and does this in the movie. Yeah, Niket, yeah, I think, yeah, I remember that. He ties around some rope to his body, I mean, his waist, and he unwounds just like that, something similar to that. So I'm going to write the torque. About the center, mg cannot create any torque because it is passing through the center only. So there is no torque there. So only tension creates the torque. Tension into perpendicular distance r. T into r equals to I alpha, t into r equals to I alpha. So t into r, my I is nothing but mr square by 2 into alpha. R cancels each other. So t equals to mr alpha by 2. Now, you can't just rush in and write a equals to r alpha. We don't know that. In the previous problem, like a pulley problem, we used to write a equals to r alpha because there was a reason. What was the reason there? We used to clearly write the constant relation saying this is going down with a. Since it is going with alpha, this point has downward acceleration r alpha. That is the reason why I simply wrote a equals to r alpha. But this is a different situation. We can't simply say a equals to r alpha, but we will get the value anyway. So I'll slowly show you that. What are the equations that we got? I'm going to repeat these equations right here. Mg minus t equals to ma, and t equals to mr alpha by 2. T equals to mr alpha by 2. We still don't know the relation between alpha and a. Remember that point, guys. We don't know the relation between r alpha and a until now. Okay, I'm going to take the model again, take the problem again. Now, we all know that the body is going down with a like this. Let me take this part away first of all. Let me take this part away. We don't need that part. It is going down with a. Let's just take, yeah, it is going, array, is going down with a, and also it is angularly accelerating. That is what we have, right? Now I'm going to write the acceleration of every particle. Now watch this thing. So this has a, this has a, this has a, we all know that. So this has r alpha like 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 this. I hope everyone's getting this point, or about r alpha. Now here is an interesting take. The part which is here, the point which is here, which is nothing but here, is basically tied to a wall. Now, what is the acceleration of this particle which is tied to the wall? We all know that the acceleration of that AP, let's just say, is 0. That specific particle which is tied to the wall, the acceleration of that particle is 0. If that is 0, the resultant acceleration, which is nothing but a downwards r alpha upwards, which is nothing but a minus r alpha, is also 0. It should be 0. So when the string, the whole thing is unwinding, you clearly understand one thing, right? Like when the whole thing is unwinding, different particles of the body might have acceleration, but this particle right here doesn't have any acceleration. It doesn't even move. It stays at rest along with the string. So, but according to our calculation, it has a downwards, r alpha upwards. So I'm going to write a minus r alpha, which must be equal to 0. From that, I have a equals to r alpha. This is how I bring the constant relation. Though, even though we got the same value from the previous situation, please don't think that they're both the same situation. They are not the same situations. We just got the same value, a equals to r alpha. So I'm going to put it there, t equals to mi by 2. I put t in there. What do I get? Mg minus ma by 2 equals to ma. So mg equals to 3ma by 2. So a is nothing but 2g by 3. So with this linear acceleration, it accelerates downward. So remember, guys, whenever you have a pulley, not a pulley, a disc wound around with a wire wound around its waist, let's just say, and fixed to a ceiling, and it is released. It simply goes down with a and alpha, and the a value is nothing but 2g by 3. Alpha must be equals to what? 2g by 3r, since a equals to r alpha. Aditya, what is it? Aniket
So
also.
once can you explain why you are not considering alpha and a equals, like why are you not using that relation? Why are you deriving it?
Okay, like there are two separate situations. I hope you clearly see that the idea of constraint relations is so important here. First of all, I'm repeating this method because of it is very important. Take this problem, take this problem. Stay unmuted only. Is the pulley accelerating in this case?
No, pulley is not accelerating.
Here the disk is accelerating, so different case completely.
Yes, sir.
Now what's happening here is this is going down with A, this is going up with A, and this is accelerating angularly. So each and every particle, this has R alpha like this, R alpha like this, R alpha like this, R alpha like this. But according to constraint relations, this point and this point must have the same acceleration. So that is why I'm taking R alpha equals to A. Okay, now remember, like, you can't randomly use A equals to R alpha everywhere. Okay, like just because you know the formula A equals to R alpha, it doesn't mean you're using it everywhere. This A and alpha are not of the same body. Okay, like you could be confused. You get sorry, something has happened. You could be getting confused because of this. Let us say a simple ring is rotating with alpha. A simple ring is rotating with alpha. So what is the acceleration of this particle? A equals to R alpha.
Yes, sir.
Now you are simply bringing this idea, but this A is the acceleration of this particle here in this case, but for a ring. I'm not talking about this case. I'm completely talking about a whole different case. I'm talking about acceleration of some block. I'm relating the acceleration of some block to the angular acceleration of a disk by using the relation of constraints. Since since the string should not should have the same acceleration along all the points, since it has R alpha and it has A, they must be equal. That's what I'm saying. You get that?
Yes, sir.
Now you're clear on the left side part. You're not
Yes,
randomly using A equal to R alpha. You're taking R alpha from the disk. You're taking A of the block. You're relating these two. Okay, so this
yes, sir.
is A of block. This is alpha of disk. Here you're talking about A of a particle and ring only, alpha of a particle and ring only. They are the same things. Here they are the different things, except you're getting the same value again. That's the point.
Yes, sir.
Okay,
Sir,
now yeah.
from that string, there will not be any resistance, sir, for all this.
No. We are still considering that there won't be any resistance and then there won't be any friction and all. Okay.
Sir, because in reality, when you do, it goes with some angles.
Yeah. In reality, it definitely matters, but we are not still there at a point where you understand reality yet. Okay, we are far away. We are in the basics now. Okay,
Okay, sir.
so let's come on to this side again. Constraint relation. We are considering a disk which is accelerating downwards and also angularly accelerating. So because of this let me take a new page and explain it. Okay, this is a very important point. So the whole disk is accelerating downwards with A. So all the points has A for sure. Okay. Now, Aditya, I'm repeating this thing. In this situation, the ring is simply at rest. Let us say it is hinged at this end. And the ring is
Yes, sir.
simply rotating. That's all. But here, there is a disk which is linearly accelerating and also angularly accelerating. This and this are completely two different cases again. Okay, Aditya?
Yes, sir. And here the string is remaining like
Yes,
rest only.
the string is remaining at rest. So this is a complete different case. But what is happening here, since I already wrote A part, now I'm writing R alpha part. R alpha here, R alpha here, R alpha here, and R alpha here. The important point is the point here on the string, the point here on the string. They must be at the same acceleration. This cannot accelerate. So AP cannot accelerate. Acceleration of this particle is nothing but A downwards, R alpha upwards. So A minus R alpha. Since this acceleration and this acceleration must be equal, that is why I'm writing A minus R alpha equal to 0. That is why I'm writing A equals to R alpha. You getting the point now?
Yes, sir. Now I got
Now,
the
what is
complete
the
picture.
acceleration of this particle? So since R alpha equals to A anyway, I'm going to write this as A, this as A, and this as A. So I'm going to redraw the diagram. Clearly watch it. We have a disk which is rolling down. So what is the like all the particles have A because of linear, And angular also, R alpha is like this only. A, A. Why did I add A again?
You just substitute the value only, no,
Oh,
sir.
yeah, exactly. This is because of R alpha, which is equals to A. This also R alpha, which is equals to A. This is also
Yes, sir.
R alpha, which is equals to A. This is also R alpha, which is equals to A. So if you clearly look at the diagram, this has a root 2A acceleration. This part has 2A acceleration. This part has root 2A. And this part has zero acceleration. Let me draw it clearly again. I have a very bad habit of making a mess out of a paper. So this part, it has A like this. So it has root 2A. This has A downward. So 2A, the acceleration of this end is 2A. The acceleration of this end, A, so root 2A. The acceleration of this part, A downwards, A upwards. So acceleration is 0.
0.
You get that?
Yes, sir.
Yeah. So,
Here, one more thing, sir, I observed.
yeah, tell me.
Like the acceleration is not constant all over the body actually.
Exactly. The body does not have the same acceleration. That is why it is a combination of linear and angular accelerations. Okay.
Yes, sir.
Right. Now, let me take you to our next point, important point here. So they
Thank you,
give
sir.
a problem saying something like this, like there is a long log, a cylindrical log on which a rope is wound like this, and they release the entire cylinder downwards. It's exactly the same problem, except you have two tensions, T, T. It's the same problem. Like you won't even, there won't even be any difference in this problem. So it's all completely the same thing. All right. But there is another problem which is really important, which is there in HC Verma. I hope you are clear with this problem. This is very easy. When you have a log, it's as if you have a disk. That's all. It is rolling down, and there is nothing that is different in this problem. Now, in the next problem, this is a problem that is there in HC Verma. Consider, don't, I mean, like this is not useful. This pulley is not useful. We are not considering that. So there is one disk of mass m and radius r. There is another pulley, sorry, another body m1. Let us just call the mass of the body as m1. Now this is not that important for, like the block is not that important, but this is right quite important. Okay. This, the sphere, that's not the sphere, it's a disc only, I guess. It actually rolls down. When it is coming down, it is actually having a linear acceleration and an angular acceleration. Okay, and again, the same point. This point has A downwards, R alpha upwards. So this acceleration is 0 because this acceleration is 0. This problem is exactly the same thing. Okay, so if only I have to write all the accelerations of all the particles in the same situation. This point on the right side point, the acceleration is 0. Can somebody tell me all the accelerations now? Right side point, the acceleration is 0. Left side point, it has 2A. This point has, it is rotating like this, right? So so root 2A. This point has A, root 2A. I hope everyone got the acceleration the way I wrote it. Like, except, I mean, in the previous situation it was on the left side. Now it's on the right side. So anyone has any doubts? This point has zero acceleration. This point has 2A acceleration. I'm stressing on this thing, very important. Please follow. Okay. So in this problem, whenever I'm drawing the entire situation, guys, can somebody tell me what's the acceleration of center of mass here? It is just A, if you remember, right from the beginning. The center of mass has only an acceleration A. That's all. It doesn't have anything from alpha. It only has A. Okay. So I'm drawing the last problem that we are doing again. There is no space there. Okay. So when this disk, let's just imagine that is a disk, when it is coming down with A and it has an angular acceleration alpha, we also have A equals to R alpha because of this point and this point. We've already made up that. What I can say is the acceleration of this particle is 0. The acceleration of this particle downwards is 2A. The acceleration of center of mass is just A. Now, from this point, I'm saying since this is 2A, this point has 2A, this whole string must have the same acceleration, which is also 2A. So this is how I bring the constant relation in this kind of a situation. This is very interesting. Like this is a different kind of a model. First, the constraint relation is important. Then we go to the problem. I hope I'm making sense to you all. First, the constraint relation is important. Then we go to the problem. So whenever I have a system like this, I directly write that this body is going down with A, this body is coming with 2A. That's all. There is nothing, I mean, like there is no strange, different kind of a mechanics here. It's a very simple problem again. Okay. Aditya, which part do you want the clarity? Can you tell me? I explained it very clearly.
So from the point when you are bringing the constraint relation to that block,
Yeah.
other
So
block.
this part you have 2A, we agree, right?
Yeah, yes, sir.
Now, if it has 2A, this point has 2A. If this point has 2A, this point has 2A. If this point has 2A, this point has 2A, then the block must also have 2A. That's all.
So will it have tension also, no, sir?
Yeah, obviously the tension will be there. I'm just talking about the constant relation, only accelerations for now. Obviously, you have to write tension 1, tension 2. Here I'm writing tension 2 only because this pulley was
Tension.
useless.
This was massless we
Yeah,
considered as, sir.
that part was considered as massless, so I don't consider that. But these two tensions must be different. Why?
Because of that mass, we have a pulley in the
Exactly right.
we have
So let's
mass in
just
pulley.
go forward with the problem, guys. This is a very difficult problem to understand. So it's totally fine if you don't understand. Jesus, watch this video again. It will definitely make sense to you people. Just write the linear equations first of all. Mg minus T1 plus T2 equals to M into A for this body. Mg is downwards, T1 and T2 are upwards. So this for this body. For this body, it is just T2 equals to the mass. Let's just take it as M1. So M1 into 2A. So these two equations are done. Now the last equation, you have to write the torque equation also to get something out of it. We imagine it is rotating like this. So T1 is supporting, T2 is opposing the torque, the body. So I'm going to write the torque as T1 into R about the center of mass only. T1 into R, it is creating this torque minus T2 into R because T2 is creating a torque like this equals to I alpha. I about center of mass only. So these three equations, I'm going to write these three equations. And obviously from the constraint relation, remember we found also A equals to R alpha also. I can use that equation also. A equals to R alpha. So I have to use all these four equations. Do you want me to do it? Do you want me to completely explain it? Aniket.
Sir, how do you know that T1 is greater than T2?
I just imagine because the body is rotating like this. Considering the rotation, I'm just saying T1 is greater than T2.
If you
Okay.
take wrong value there, nothing will happen, right, sir?
No, no, nothing will happen. But once you took the rotation in a specific direction, stick to that thing. Okay. Like I already considered that alpha is in this direction. So I'm just sticking to that. Okay, Aniket?
Okay, sir.
Yeah. So like, do you want me to
Okay.
solve this thing, whole thing? Is it important? Okay, Zaid is asking. So I'm just writing all the equations down here one by one. Mg minus T1 plus T2 equals to M into A. And then this T2 equals to M1 into 2A. This equation is done. This equation is done. I'm going to write this. T1 minus T2 into R equals to MR square by 2 into alpha. and also a equals to r alpha. So I'm repeating, I'm just removing this alpha and writing a by r. R cancels, R cancels. The equation simply becomes T1 minus T2 equals to MA by 2. So we just don't need this equation anymore. All you need to do is solve the equation that we have right here on the screen. There is not much of work that we need to do here, I guess, because all you need to do is simply add these equations, I guess. Or no, you actually have to solve these three equations. You know how to solve the equations, right? So you do simply solve the equation, find the a value. From once you have the a value, you can find the alpha value and all. You can get the answers easily. Okay, so this is a long method, this is a long procedure, but this is an important procedure that you need to understand. Now the takeaway from this point, okay, solve any two equations, you'll get it. No, I don't think so, because you have m1 also. I don't think you will simply get the answer. You have to solve all the three equations. Now the takeaway from this problem is very important, is it's that the constraint relation only, the thing that I hope you clearly understood this part. The takeaways from this problem is clearly this, because this is going down with alpha and a. I hope you clearly see that bit. So once you have this, the thing that you need to understand, this acceleration is 0, this acceleration is a, this acceleration is 2a. So it is causing it to come at an acceleration 2a. This is what you need to clearly understand. Okay, once you're clear about this part, I mean, this is a very big problem to remember, so I just wanted to discuss this. Let's go back to HCFM problems. Like, this is a problem that I just discussed, 37. Okay, so when you're doing this problem again, like, do this problem again. Take the values and try to solve this problem again and make sure you get the answer. Okay, 38 is easy, 39 is easy, and all these problems are not that difficult anymore. Except coming to this side, I don't know where is this coming from. There's a lot of water in my laptop. Uh, the problem which is 43, which is 43, 44, 45. These are some new models. We haven't discussed these kind of models. I want to discuss these kind of models using torque only. So kind of model they say is very simple. There is a this we are actually going back to the torque equilibrium problems. Equilibrium problems only. These are, we are not discussing new problems. We've already done this. We are done with the equilibrium problems already, but these are some good standard. There is a ladder which is resting against the wall. There is a ladder which is resting against the wall. How does the ladder first of all rest? It has some weight. It has some weight. It must I mean, simply accelerate, right? But we have some normal force. We have another normal force from the wall, but still the ladder will slide. There is nothing to stop it. So that is why the friction here is so important. So there is some friction here. In some cases, there is friction here also. So this entire problem, these entire problems are really fun. Let's discuss some of the problems like this. But let's start with a basic problem. Okay, we don't need the friction here. We don't really need friction here. It's totally possible that without this friction also the ladder can stand. Let's just take a problem like this. Okay, uh, I'm already giving the values, random values, so you get your pens ready. Why is it behaving weird? There. So there is this ladder. Okay, let's write all the equations. Okay, basic values only. We don't write anything stupid. Mg, normal force 1, normal force 2, and this is the friction acting on the body. Now, to talk about the equilibrium of the body is not linearly accelerating. The body is not angularly accelerating. It is basically at rest, right? So all you need to write is, you simply have to do is F net equals to 0, torque net equals to 0, tau net equals to 0. You simply have to write F net equals to 0 and tau net equals to 0, and that's all. First of all, let's start with F net. What are the forces acting vertically? Mg and N1. So I'm directly going to write Mg equals to N1. What are the forces that are horizontal? There are two horizontal forces. One is friction, other is N2. So F, let us call this as F1, okay? Because it is N1, let us call it as F1. So the friction F1 equals to N2. The linear equations are done. And most of the situation, the problem is done here itself. We don't really need a lot of values, but sometimes they don't give all the values. So we might need to write the torque also. Now, writing the torque is an interesting idea here. You can literally choose any point here. Okay, you can choose the torque about this point randomly. Okay, so I'm going to teach you how to write the torque. I'm going to draw the diagram again. You can write the torque about any point. There is nothing wrong in writing the torque at any point. Okay. Mg, I'm going to write N1, N2, and then friction. So what I'm saying is I can write the torque about this point. So what will be the torque like? Mg into this perpendicular distance, N1 into this perpendicular distance. The torque due to friction is 0 because the friction is passing through that point. Clearly understand that? And N2 into this perpendicular distance. You have to write all the torques. You have to manage the directions also, whether it is positive direction or negative direction. You have to be careful. Okay. You can write the torque about the center also. But there is a reason I'm actually choosing this point to write the torque about. Can somebody tell me why? I'm choosing this specific point to write the torque. Raise of hands, please. There's a reason why I'm choosing that specific point. Why?
So you can cancel out N1 and F1
Not
from there,
cancel
sir.
out. We can ignore the torques because of
Yeah, ignore. I mean to say ignore only,
we
sir.
can we all we need to write is the torques because of these 2 points. That's all. Okay. So this is
Yes,
like
sir.
a technique that we use. Okay. Writing the torque about some specific point is just like an art that you need to learn slowly. Okay. As you get better with this topic, you'll understand about which point it is better to write the torque so that the calculations get lesser. Now you can choose any point and write all the torques, but I don't see any point there. Okay. There's just no point there writing all the talks about all those points. So I'm writing Mg here. I'm only writing N2 only. I'm not even mentioning these 2 points because about those, I mean, that about this point, the talks are 0 anyway. So I'm not even mentioning those forces. Mg into this perpendicular distance. We already know this length is L by 2. They have to mention theta, obviously. So this is L by 2 cos theta. So this torque is clockwise. So mg into L by 2 cos theta. Mg into L by 2 cos theta. Now N2 into this distance, which is nothing but this whole length is L. This is L sine theta, obviously, because this is theta. So this is L sine theta. And the torque is anti-clockwise. So N2 into L sine theta. That is the anti-clockwise torque. This is a clockwise torque. This is the anti-clockwise torque. I have to equate them to get the balanced equation. So Aditya is asking, sir, should there be friction between the ladder and the vertical walls also to make the ladder stand? No, you don't really need this friction anywhere. I mean, like there are situations where there is friction here also, but even though without this friction, it can stand. Like you don't, it won't slide off, right? This friction will clearly stop it. This friction will clearly stop it, so you don't have to write that torque. Okay. Now, be quick, be really quick, and do me a favor and find me the answer for this problem. Okay. The question goes like, uh, this angle is 37 degrees. I hope you remember the values of sine 37 and cos 37. I'm writing them anyway. Sine 37 is 3 by 5. Cos 37 is 4 by 5. This is 10 kg ladder. find the mu value here, find the mu required here so that the ladder is stable. That is the question. Find the mu value here so that the ladder is stable. Where do you use the mu value? If we go all the way to these forces, mg is n1, that is fine. But when you write f1, the friction 1 is actually depending on n1. So mu n1 equals to n2. This is one equation. These are the two equations that we are going to use. This equation and this equation. This is this only, okay? So we have one equation here, two equation here. So mu n1 is nothing but n2. I want the value of mu in this problem. The problem is on the screen right now. 10 kg ladder, 37 degrees. I want the value of mu so that the ladder stays stable. Do a quick calculation as quick as possible and let me know the answer. Oh, sorry. I think also I need to give the length. I don't think I need the length. Anyway, I'm giving the length to make it much easier. 5 meters. Do Pandag since it is 5 meters. Harshavardhan says the answer is 200 by 3. What is 200 by 3? Mu value is less than 1, you stupid. Mu value must be less than 1. I want the mu value, only mu, that's all. Sai Vamshi also gave some answer saying, Acha. Okay, guys, first of all, answer is coming as 2 by 3. Okay. Two people gave the answer as 2 by 3. I'm not sure if the right answer is, if that's the right answer or not. Okay, 3 people says the answer is 2 by 3. Come on, guys, is there anyone who's getting the same answer? Okay, everyone's basically getting the same answer. It's very simple, right? The problem is very simple. All you have to take is mg n1 n2 and write the values mg equal to n1, f1 equals to n2 and write the torques because of mg and n2 and that's all. Okay, this is an easy way to do this problem only. It's not that difficult. Okay, guys, once this part is done, okay, people are getting the answer. I don't think I need to do this thing. Mg equals to n1, f1 equals to, which is f1 is nothing but mu n1. So mu n1 equals to n2. I have these two equations. That is one thing, and also this equation, which is similar, like mg into L by 2 cos theta, right? L by 2 cos theta equals to n2 into L sine theta. So you simply solve these these three equations, you'll get all the values that you need. Okay. Now the problems get a little more tough. The problems get a little more tough when a man, the lift or the ladder already weighs something, and the man stands here for some reason. There is no difference at all in this problem. They also mention where the man is standing, at what distance. Once the man is standing, you simply add his force and add his torque also, and you solve the problem. Once a man is added, you also add his force and his torque, and you'll get the answers. So there is no difference in this problem at all. They simply ask you, the man is standing somewhere, what is the value of mu and all. Sometimes they give you friction here also, so you might have to take mu n2 also. There are some problems where they ask that friction also, so you need to be careful on that problem. All right, now after this you will definitely ask me one more problem that I know. I'm going to give you some hints on these two problems, okay? On problem number 44 and 45, there is an almara. Almara is nothing but a door. There is an almara 6 feet height and all. These two problems you will definitely ask me because in every batch everyone asks. I'm just going to give you some hints. So there is a rectangular almara, let us just say door. It is fixed at two hinges, and it is basically an equilibrium problem only. All you have to write is mg downwards and normal forces. Everyone fails at this point. They only take the normal force like this only. But like I mentioned, a hinge can offer normal force in any direction. In most of the situation, it's just vertical, so that's why we take vertical. But in this situation, remember, this is ny1, ny2, nx1, nx2. The reason why I'm taking nx1 and nx2 in the opposite directions, if only this nx2 is also in this direction. There is no horizontal force that balances the almara. So for this problem, like when you're doing this problem, you'll clearly understand why I'm doing this all. But just remember the point that take this normal force in the opposite direction, nx1 and nx2, and solve the problem, you'll clearly get it. And in the next problem, they make a ladder or a wall or a rod or whatever it is, they make it stand like this. Okay. In this problem, the important idea is mg is clear, n1 is clear, n2 is acting in this direction because the contact, look at the contact, look at the way they contact each other. N2 is acting in that direction. So that is how that you do that specific problem. Okay. So up to that point, up to the problem number 45, I want you to practice today. Now going to 46 and 47, it's all about angular momentums, which is a topic that I'm going to introduce tomorrow because I thought I can introduce it to you today itself, but it's already way too long. This class is way too long. I'm just going to give a brief idea about angular momentum. Okay. Very brief idea about angular momentum. We already know linear momentum equals to P equals to mv. They simply define angular momentum as r cross p. So r cross this mv bar, that's all. But we will slowly get into the depths of this problem. Just like torque, we have r cross f, we have r cross p, and everything is simply related, and we will definitely get into this topic tomorrow. Okay, it's not that big of a topic. This is fun. Like from this point onwards, problems get really fun, so we will slowly get into the ideas. All right, so that's it, guys. That's it for today. Are there any doubts just from today's topic? Just from today's topic, are there any doubts? Please raise your hands. Nothing, I see. So I don't see any problems from just today's topic. So we will meet again tomorrow, and we will discuss the idea of angular momentum from tomorrow onwards. All right. So thanks so much, guys. Thanks so much, and bye bye.